Okay. So today we're going to talk about something called implicit differentiation. Up until now, we've been doing explicit differentiation because it's always been f of x equals something with x's, or y equals something with x's, where all of your x's were grouped together on the right side of the problem. With implicit differentiation, what happens is you have x's and y's all over the problem. What you do is you have to differentiate both sides, and then you solve for your first derivative. And when you solve for your first derivative, this is where you use that dy dx notation I talked about, because every time you have a y term, y will always have a chain, and its chain is going to be dy dx. X does not have a chain, because you're taking the derivative with respect to x. X's chain would be dx dx, which is just 1, so we never write it down, okay? So, in terms of the steps for implicit differentiation, you need to differentiate both sides with respect to x. Y will always have a chain of dy dx. Then what you do is you get all of your dy dx terms on one side. With the other terms on the other side. And you need to factor dy dx out as your greatest common factor. And divide by the rest. So after you have taken the derivative, often you end up multiplying some stuff out, because what you need to be able to do is you need to be able to freely move things from one side of the equal sign to the other side of the equal sign, so that you can group all of your dy dx terms together, and then you can factor out and divide. Right now, when you do this, you're going to have to show quite a few steps. Eventually, you sort of learn the way the problems work, and you can skip a few of the steps. Or maybe you can never skip a few of the steps and you have to show it all, which is fine. Just make sure that you're careful with what you're doing. So, we're going to do a bunch of examples. And then we're going to do a couple of second derivative examples. Second derivatives can get kind of horrifying. Not always, but a lot of times the simplifying is hard. What you need to remember is that the calculus in these problems is usually not too terrible. It's the algebra that kills people, okay? So make sure that you watch what you're doing in terms of your algebra. So we're going to start with a couple that are pretty simple, and then we'll make them uglier. This one is going to be super, super easy. So you're going to take the derivative of both sides. So the derivative of x squared is just going to be 2x. The derivative of 3y squared, you have 6y to the first, and then it's y, so you would chain it, and its chain would be dy dx equals nothing. And then you're just solving for dy dx, so you would subtract the 2x, and then divide by the 6y. Please don't leave it negative 2x over 6y. Reduce your numbers. And that's as simple as that one is, okay? Sometimes they are. They're pretty simple, and sometimes they're kind of horrible. But this one's not too bad. Next one. Okay, so the derivative of x to the fourth, you get 4x cubed minus, here you've got x and y, they're next to each other, and a product, so you have to do a product rule, even though we're doing implicit differentiation, which is new, product rule, quotient rule, still things, okay? So, product rule, you've got first derivative of second, derivative of y would be 1, and then you have to chain it, minus, because I'm distributing the negative, second, which is y, derivative of first, which would be 1 plus, it's going to be 3y squared dy dx, because you got to chain it, equals nothing. So at that point, these two terms get to stay on the left side. I like to leave my dy dx on the left side. And your other two terms need to move to the other side. Now, here is where I'm, I don't know, picky, idiosyncratic, however you want to say it, about what I do. Because I'm leaving these two terms here, this is positive and this is negative. I like to lead with my positive term if I possibly can. If you go, I don't care, I want to lead with the negative term, it doesn't matter. It makes no difference whatsoever. My guess is that when I learned this in high school, that was how I was taught, so that is what I've stuck with. I like to keep things positive, I think it makes them pretty. So same thing, when I move this term and this term to the other side, instead of writing negative 4x cubed plus y, I'm going to put the y first. Does it make any difference whatsoever? Not a one. Okay? So then you're going to factor the dy dx out, because now it's the greatest common factor, and that's how you want to view it. Because then what that allows you to do is it allows you to solve for dy dx, which is your first derivative. What you want to notice with these problems is if you're ever looking at the answer, and what you notice about the answer is you have exactly the same thing, but every single sign is switched, it's still the right answer. Because what happened when that occurs is that when I put things on the right side, you left them on the left side, and vice versa, which is how you can have the exact same thing with all of the signs switched and still be right. Okay? Next one. So, same thing, you have to take the derivative. Derivative of cosine of x is going to be negative sine of x. The derivative of this, you're going to end up with 3 cosine of 4y plus 3x. And then you have to chain it. So the derivative of 4y plus 3x is you're going to have 4 dy dx plus 3 equals nothing. Fine. So you're trying to figure out how to get to this. Right now it's trapped by this whole thing. So what you're going to do is you're going to take this and you're going to distribute it like it is the ugliest 7 in the world. Okay? So when you distribute it, it's going to plant here and here, and you're distributing the whole thing. You can't just distribute this part, because it's not math. You can't ever distribute the word cosine, because it's not math. What I like to do when I'm distributing an entire chunk like that is I always like to plant my dy dx at the very end of the term, because I like to pretend, sort of, that it's the variable and everything else is just an ugly, ugly constant. That's why, like here, I had it be 3y squared and then dy dx. I could have put it anywhere in the part, in the term. I just like to always make sure I put it in the back so that I know what I'm looking for. So negative sine of x does nothing interesting. But this I'm distributing. So now this times this, you're looking at 12 cosine of 4y plus 3x dy dx plus 9 cosine of 4y plus 3x equals nothing. Now you're just moving stuff. So you're going to move over that one, and then you divide. If you get good enough at this that you can do this in one step and just write the answer down, fine, as long as you're doing it right. I don't care how many steps it takes you, okay? If you're doing it deeply wrong, then show the steps. What you'll notice on worksheet keys is I tend to try and get through this in as few steps as possible, only because I feel like the more times you rewrite it, the more likely you are to goof something up. So we're moving the sign of X over, and that one. And I wrote the sign of X first because it was positive, and that's what I do. So then we're just going to divide by all of that like a chunk, and that will give you the first derivative. More practice. Okay, so I wrote them both down, so I don't have to keep going back to the book. Here, same thing, you gotta chain it through. So the first thing you're gonna do is you're gonna pull the 2 down. Now it's to the first power. And then you'll deal with the inside part. So here, derivative of sine of 4x is going to be cosine of 4x times 4. Fine. Minus sine of 5y is going to be cosine of 5y times 5, and then it was y, so you'll chain it, equals 7. Fine, so here's the deal. In the bookwork, you have a homework problem where it doesn't equal 7, it equals 0. When it equals something like 0, what you want to do is you would take all of this and you would just divide it away. And then it's gone, and you're just dealing with the stuff in the set of parentheses. I was cruel and made it equal to 7, so you're going to have to FOIL everything out, because this is deeply trapped. And there's no good way to get to it and leave your answer as sort of dy dx equals one chunk of stuff, which is how these problems should be structured in terms of their answer, unless you do a lot of multiplying. So I throw the 2 into the parentheses, and then do some FOIL, and it's just going to be gross. I should have written that further that way. Oh well. All right, so now you got to move stuff over. So this one and this one don't have the dy dx attached, so you would scoot them over. And now, in the interest of not having to rewrite this a bunch of times, I know that these 2 terms are going to be left on my left side. I'm going to factor the dy dx out as I write them down. You don't have to. You could rewrite it a bunch of times, but I don't want to because I feel like if I have to write 5x and 4y, vice versa, a million more times, I'm going to goof it up at some point. So same thing. I'm also going to put this one first because it's positive, and I like to leave my positive stuff in front if I possibly can. I really would not have had space for that problem. Oh well. So now you can divide by the nonsense that's in the parentheses, and then you'll be done. So it's kind of ugly, but you know. Like I said, that's why I try to avoid rewriting the problem 30 times if I can. Plus my handwriting is bad enough as it is, and rewriting it a million times does not make it better. Done. Okay, 4 more. 2 second derivative problems, neither of which are too terrible. And these are nice. I like to do a lot of them so that you see them. It's a video. I guess you don't technically need to watch them all, unless you get stuck, in which case they help. So, derivative, you'll pull the half down, then you have xy to the negative 1/2. Then you have to do product rule between x and y, because it's a product. So you got first derivative of second, plus second derivative of first. Then here you've got 3 minus 14y 2y dx. Okay, so, specific rules when it comes to implicit differentiation. You cannot leave negative powers in the overall problem. You have to fix that. So that xy to the negative 1/2, not great. You can't leave it like that, okay? So if it's to the negative 1/2, what that means is that you have a square root on the bottom. Specifically, you have the square root under the x dy dx and the y term. So you want to put them underneath that, and I like to pull the 2 from the half underneath there too, because I feel like it makes it less awkward looking. Because then what you can do is you can take this 2 square root of xy and multiply it over. And then distribute it into this, okay? So then you've got x dy dx plus y equals, so if we're taking it and doing, then you've got 6 square root of xy minus, times that you're looking at 28y square root of xy dy dx. And now it's not super threatening, you just gotta move stuff around. So you gotta move the 14y term, or what was the 14y? The 28y term over, move this y over, so we're gonna move those 2 terms. And same thing, in the interest of not having to rewrite the problem again, I'm going to factor the dy dx out as I go. You don't have to. You can rewrite it again. It's not wrong. It just saves me time to not have to. So then I've got x plus 28y square root of xy. And then this is going to be 6 for xy minus y. And then you just divide. do 2 more instead of 3. We can move without this next one. All right, so when you are doing first derivatives and implicit differentiation, you want to avoid quotient rule at all costs. It will make everything worse, and it is harder to free yourself up from when you're doing quotient rule. To avoid doing quotient rule, one good thing to do is to simplify the problem in the beginning before you start taking the derivative. So like for this one, instead of doing quotient rule on the left side, I'm going to take the y plus x cubed and multiply it over to the right side, multiply everything out, and then I won't have to do quotient rule at all. I'll just have to do product rule. Once, yeah, which isn't bad. So we're going to take this. Multiply it over, and then FOIL this nonsense out. And what would have been a relatively ugly problem is now going to be pretty simple, where, like I said, we only have to do product rule once, which is really cool. So we got 2x minus 2y, and then you chain it through. Product rule, because it's a product. And then you've just got to move some stuff. So this is going to have to move, that's going to have to move, and that's going to have to move, so that all your dy dx terms are on the left. You technically can put them on whatever side you want. I like to leave them on the left. The same thing, I pretend it's a variable, so it's what I'm solving for, so I leave it over there. I'm going to write the 4 first because it's positive and I'm weird, and I'm going to pull the dy dx as I go, so I don't have to keep writing it down. So I'm moving the 4 and the x, the 2y is there already. So then on this side, you have the y, the 4x cubed, the negative 12x squared, and you're moving the 2x over, and then you just divide. One more, and then the second derivative stuff. Second derivatives are really the exact same concept. They get harder because sometimes the algebra gets a little crazy. Alright, so same thing. You look and you say, look, I can do quotient rule twice. Don't do it. It would be a terrible, terrible idea. What you need to do is you need to make common denominators on the left side and then multiply your common denominator over. And then the problem is really not that bad, okay? So, this term is going to get the 2 y's. This term is going to get the 2 x's. Fine. And then you just multiply to the other side. And what was an ugly, ugly problem, similar to the last one, now requires you to do product rule once, which isn't bad. So here you've got 3y squared dy dx, because you got to chain it through, plus 3x squared equals, and then you got to do product rule. So you got first derivative of second plus second derivative of first. And then you just gotta move stuff. So this will move, and then you'll factor out and divide. The same thing, if you can swing it in one step, do it. If you go, no, that's terrible, many, many steps, then do all the steps. Divide. And I know I said it once, I'm going to say it again. Remember, if you're doing these problems and you notice that you have the exact same answer, but all of the signs are switched, it's the exact same thing. It's just the left versus right of it as you were doing the problem got switched around. All right, second derivatives. There's one of these, just as a heads up in your homework, that is kind of awful. You just gotta really make sure you take your time with it. So this is the implicit differentiation notation for a second derivative. They want it to be in terms of x and y. Fine. So first thing you have to do is you have to go through and you have to find the first derivative. Okay, so then you got 2x plus 2y dy dx equals nothing. Subtract 2x over. Divide. Get rid of the 2's, don't leave them in. It makes everything worse and you just look sloppy. Fine. So now you have to find the second derivative. Often, probably always, when you go to find a second derivative, you're gonna have to do quotient rule. You avoid them at all costs when finding the first derivative, but sometimes with the second derivative, you just live with it. So this side will automatically change into your second derivative. This side is going to require you to do quotient rule. So you've got bottom derivative of top minus top derivative of bottom over bottom squared. Okay, so here is where the simplifying can get tricky, because what they're asking of you is they need it in terms of x and y, not x, y, and dy dx. So you can't leave this like this, okay? But you already know what dy dx is in terms of x and y because you found it already. So then you're going to take this and plug it in, and then just simplify it so that it looks nice, which can be the really, really hard part. Not for this one, but sometimes. So if you here have x times negative x over y, and you're looking at minus x squared over y squared. So same thing, at this point you're going to make common denominators, so we don't want the compound fraction, it's just yucky. And then take this and pull it down. And that's it. All right, so one more second derivative problem, then I want to give you a piece of advice about tangent lines that you should definitely write down when I get there, and then that'll be it for implicit differentiation. Okay, so same thing, derivative of 3 is nothing. Here you have to do product rule, so you've got first derivative of y would be 1 and then dy dx plus, but really minus because you want to distribute through. Second derivative first is going to be 2 minus dy dx. So this will move, and you want to factor it out. Or take 2 steps and factor it out in a minute. Remember, when you add this over and then factor it out, the term does not disappear. You have 1 here, you'll have y plus 2, or 2 plus y. Again, it doesn't matter. Divide by this. Then you have to find the, right here, second derivative, where you're just going to have to live through quotient rule. So you got bottom, derivative of top, minus top, derivative of bottom, which would just be -1, so we'll fix that. Over your bottom part, squared, and same deal, we'll plug in. Okay, so notice here, instead of having the common denominators, you can cross this out. Then you just have this and this on top. So then you're looking at 2y plus 4 over 1 minus x squared. Okay, so last thing that I want to say about implicit differentiation has to do with tangent lines. When you are doing implicit differentiation and tangent lines, what you have to do for tangent lines, remember, is you have to plug in the x value. Make sure when you're doing implicit differentiation and tangent lines, after you have taken the derivative, plug everything in and then solve for dy dx. Don't solve for dy dx and then try to plug in. If I was doing a tangent line problem for, say, this, and I never had to find the second derivative, I would have plugged the numbers in here, not once I got here, okay? After you've taken the first derivative, before you simplify anything, plug everything in, and then you're working with numbers, and the problem will ultimately be much simpler, okay?